Hello, everyone. We have 55 people. Great. Okay, so yeah, so you can hear me, I guess. Can you see my screen? It says homogeneous coordinates and it has the dragon. Great. Perfect. Okay. So today we have several learning goals. By the way, give me a second. Yeah, Nam was sharing a YouTube video about his group, so please check it out. I mean, after the lecture, not right now, but it is amazing. I guess Nam, I guess you are working with Michael. I guess yeah, your guys are always doing amazing job. Yeah, yeah. At the very beginning of the chat, Bo, there's a link, but don't worry. Maybe yeah. So yeah, I can even maybe share it, or Nam, if you can share it, maybe at the end of the lecture, it will be nice. So I recommend to see the video, but again, at the end of the lecture. Okay, perfect. So let's start. So the learning goals for today, we have this. Okay, so we will talk about homogeneous coordinates. We already used them last class when we were talking about affine transformations, but I haven't explained where they come from. So we will talk about that, and we will talk that those homogeneous coordinates are basically something it comes from something called projective geometry. And we will talk about projective line, the projective plane, and another important difference between vectors and points. And maybe also at the very end of the lecture, depending on how much time do we have, I will show you an example of the theory assignment 2 that basically is releasing today. We're releasing that today. And yeah, so we will talk a little bit of that, because maybe some parts of that theory assignment could be confusing for some people. Okay, so first thing, if you go to the web page, well, if you were seeing the web page since yesterday, you probably noticed that I uploaded the theory assignment 2, but I just remove it right now because Jake, if you remember, Jake is one of our TAs. He just saw that I was actually using, I think, a deprecated version for some of the 3.js code that is on the assignment. So I just removed the assignment, and I need to modify that. I need to fix it, and then I will just re-upload the PDF after the lecture, right? So if you don't see the assignment right now, if you see it before, if you already download the PDF, just throw it to the garbage. That PDF will change, and I will modify it and I will upload it after the lecture. Yes, I released it last night, sorry, but again, it has a tiny mistake that I need to fix. So the correct version will be available after the lecture. Okay. Good. So yeah, so last class, in our last lecture, we were talking about. Give me a second. Let me just hide the chat for now. So remember, I will not read the chat. Also, TAs will not necessarily reading the chat, right? So we'll have pauses for questions, and you can raise your hand. Okay. So we were talking about what happens when we transform vectors in the wrong way, or in this case, what happened when we translate vectors, right? So remember, vectors indicate direction or motion, right? And they are basically constructed by the same elements, right? They always have the same elements. Conceptually, we know already that a point has an associated vector, right? And a vector, we could say that conceptually it has kind of 2 points, right? Because it has like its origin and also its goal, its tip, the tip of the vector. However, we always use exactly the same structure to define the same these different objects, right? We use the same x, y, z data to express either points in 3 dimensions or vectors in 3 dimensions. So if we translate a vector, it's like moving only the tip, right? We are not moving the origin because the origin is not in our data. We are just moving the tip. And that is wrong because basically we end up with, in this case, maybe normals pointing to a different direction. So one of the way we can solve this is that last lecture we said, okay, let's just add another dimension to this structure. And instead of having only x, y, z, we will add another dimension that we call w, right? And that dimension will have a number 1 for points and a number 0 for vectors. And with that, then we augment the matrix or transformation matrices, and now they are called affine transformation matrices. And basically they contain a linear transformation, and this thing of adding another column and another row, right, and another element to points and vectors allows us to basically use exactly the same matrix, so we don't need to change the matrix, but we can use it with points. Basically we are adding translation, and we also can use it in case of vectors, and vectors, because they have 0 on the w value, they will basically remove the translation, right? So that is what we said last time. Okay. But I was also telling you that adding those extra dimensions is not only a hack, because it seems like it's a hack. It's like, yeah, it seems like we just add something to our data and now we can use 4x4 matrices. But the thing is, they come from other like conceptual stuff that is important in computer graphics. So those coordinates in which we add another w value, right? Those augmented coordinates are called homogeneous coordinates, okay? And I will tell you where they come from, okay? So these coordinates are part of something called projective geometry. I will not give an entire lecture of projective geometry because you could have an entire term of projective geometry, and there are a lot of videos in YouTube or in great books about it. But let's just take the enough information from projective geometry to understand what are homogeneous coordinates. So let's imagine that we have a 2D space, right, with x and y coordinates. Okay, so this is a planar 2D space, and it could seem, or it's very similar to a Euclidean 2D space, but let's not call it Euclidean. This will be a homogeneous 2D space. Okay, so we can add something to our space. This line here, right, is a one-dimensional subspace. It's just a fancy name to represent a line, an infinite line that is basically passing through the origin. Okay, so yeah, those things, or this entity here, an infinite line that is passing through the origin, is called one-dimensional subspace. So if we want to like study or cover the entire space, the entire 2D space, we can see that there are basically infinite number of one-dimensional subspaces, right? Do you agree with that? And now, yeah, and I think on this part, I will open the chat because I will probably ask you some questions. Yeah. So everybody agrees that we can create an infinite number of one-dimensional subspaces in this homogeneous 2D space? Say yes if you agree, or say no if you don't agree. Yes, perfect. Okay. So then we can also say, or we can also observe that any point on this space, right, is also inside of one of those subspaces, right? And for every point, right, there's only one-dimensional subspace that is touching that point. Do you agree? And again, you can say yes. Perhaps. Okay, someone says perhaps. Do you have a can is okay? What about the origin? Okay, good question. But it's the same, right? I mean, if you have the point on the origin, these lines are passing through the origin, right? So yeah, that is a very good observation. The only point that has that don't have a unique one-dimensional subspace is the one on the origin, right? Everybody agrees with that? Yes, excellent. So every other point, which is not 0, 0, right, has a unique one-dimensional subspace, right? Everything else, yes. That's we call null space. Danny, oh, I don't remember. I mean, yeah, maybe. I'm not an expert in projective geometry, and sometimes in different areas of math, we use different terms. So yes, I cannot say that that is true. Yeah, but I can search a little bit, and I will tell you later. Yes, only applies the concept of transformation. Someone is asking that only applies in the context of a transformation, right? Well, I'm not talking about transformations yet, right? So right now, I'm only talking about a space with points, and we are saying that the infinite number of points in this space can be mapped to one-dimensional subspaces, and that each point on that space have a single one-dimensional subspace, except for the one on the origin, which basically is, it has the entire set of one-dimensional subspaces, right? And so when he's saying, Mark is saying, however, there can be infinite many points on the same line. Yes, exactly. We will be there. Yeah. Okay. So let's keep going. Okay. So now let's create a line that is passing through the coordinate x equal 1. Okay. And this line will be called the projective line. Okay. So let's see what happens with this projective line. And before that, let's just understand something that is also important. So let's imagine that this is the subspace called A, and this is B, D, whatever, right? I mean, again, I just drew them in different rotations, but remember there are infinite number of subspaces, right? And these subspaces have are basically the same. This subspace is basically the same on this side, right? Because it's an infinite line. So basically, from taking the x-axis like as a mirror plane, right? Everything that is on one side is basically mapped with exactly the same subspaces on the other side, right? Because the subspaces are basically going through the origin and going in in both directions. So let's see what happens with this projected line. This projected line, almost every line or every subspace, right, on this space has a corresponding intersection with this projective line, right? So there's only one one-dimensional subspace that is actually not touching the projective line. So for example, imagine this one here, it will just go, right? They are infinite, right? I mean, it's going outside my view, but it will touch the projective line maybe here. This one will be very, very far outside my monitor, and it will eventually touch the projective line. So can you tell me which one is the only one that is not touching the projected line? Yes, x-axis, origin, exactly. Yes. So the one with the y coordinate equal to 0, basically, or the x-axis, exactly. Okay, good. So now, so conceptually speaking, this line acts like the infinite point. What happens here? This is like the interesting part of projective geometry and a projective line, is that we are taking an entire space that is 2D, and we are mapping an entire 2D space in a one-dimensional space. Okay, because again, every point, almost every point on that space can be mapped to this specific line. Do you agree? Almost every point, right? So the only points that are not able to touch that line are basically the infinite points, or the ones that we consider, oh, that point is at infinite, okay? Are the ones that are on the y coordinate equal to 0. Okay, Good? Yeah. Y equals 0. Thanks, Laura. Yeah. Okay. So then, as someone already said, if we only see one of those one-dimensional points, right? You can have an infinite number of points in each of those lines, right? But because that line is only touching in one single point, the projective line, all these points, all these blue points here, and basically all the set of the infinite set of numbers that are in this line have a single coordinate in this space, in this one-dimensional space. So in this case, this 2D space is it's a 2D homogeneous space, and this one is a one-dimensional Euclidean space, right? And again, all these points will have the same coordinate on this space. And that's why they are called homogeneous coordinates, because basically they have the same coordinate. Okay? So everything good here? Say yes. Otherwise you say, I have a question. Great, Tommy. Okay, so Tommy, can you raise your hand and I can unmute you, please? I can't see. Okay, nobody is raising hand. Okay, I will read the chat. So someone is saying, could you repeat what you say about the projective line and the 1D subspace? And Poe is asking, could you explain all the points have the same coordinate again? Yes, okay. So let me come back. Okay, so let's see this first. We said already that all the points on this space, except for the one on the origin, right? All the points in this space correspond to a single one-dimensional subspace, which are these lines, right? So instead of saying one-dimensional subspace, I will also say lines. Every time I say lines, I am referring to these one-dimensional subspaces, right? Otherwise, just my phrases are like super long. Okay. So every point, right, on this space, except for the origin, has only one. It is associated with only one of those lines, right? And all those lines except for one can touch or can be mapped to this other line, which we call the projective line. This projective line is basically the line in which y is equal to 1. We will see why that is, why we choose the one with y equal to 1, and why we don't choose the one y equal to 2 or y equal to 7 or equal to whatever. You will see that later, very, very later. But for now, just keep that in your mind. Okay, the projective line is the one in which that coordinate in particular is equal to 1. Okay, and there's only one of those lines that can touch that line. Is the one that is parallel to that one, right? The one that is basically the x coordinate, or the one from which all its points have coordinates y equals 0. For any other point, for any other lines, we can map them into this line because they are basically like crossing that line. Okay, so is that clear? And Kai, I will explain the difference between. In the end, I think we will understand the difference between homogeneous and yes, how does? Okay, good. So, and I was saying also that all the points that are on this line, all the points whose coordinate y is equal to 0, on this specific space, they act as the infinite points. Okay, So this is the one, again, this is the one that is not touching the projective the projective line, sorry, the projective space, and this one acts as infinite. So let's now study this specific line, okay? Again, this is an infinite line that is passing through the origin, and it's a one-dimensional subspace that we are calling lines for now, just to make it short. And it's passing through this projective line, right? So what I was saying is that it doesn't matter the position in 2 dimensions of these points, any of these points in this line, it doesn't matter its 2D coordinates when they are mapped into this space. Imagine that when we translate homogeneous coordinates from 2 dimension to Euclidean coordinates from 1 dimension, it's like collapsing the space, right? So imagine that what we are doing here is not just computing the intersection between a line and another line. What we are doing by computing this point here is like taking the entire space, the entire subspace that is represented by this line. Can you see my cursor, by the way? Say yes if you can see my cursor. Yeah, okay. So it's like taking this entire space and collapse this space in this single dot. Okay? So all the points that before they had a coordinate x and y, right? Now they will also have a single coordinate x on this space, right? This is a different world. This is a different space. The projective line is a different space. Is there a particular reason you can choose that line, or it's random? No, it's not random. We always use one. And again, you will understand that later, why we choose the one that is, why exactly one, okay? Someone is saying rays. Yes, this is similar to a ray, yeah, but ray in computer graphics is something different, but yeah, a ray. The thing is, a ray, usually in computer graphics, we understand a ray as an infinite line, but that it has an origin. So rays are not infinite. Rays have a direction, and they are infinite in one direction, right? But they start from one point in particular. So in that case, this subspace is like having 2 rays, one in this direction and one in this other direction, right? So yeah, maybe making an analogy with rays is kind of weird. It's just infinite to both sides, okay? So someone is saying, so the points that intersected with y = 1 are now projected onto the yellow line. The ones on the yellow line are now projected into the pink one. Okay? Let me continue, and maybe with the next slides it will be clear. Okay, so how can we translate from this 2D homogeneous coordinate to a 1D Euclidean coordinates? I'm sorry, and this should not be here. This should not be here. Give me a second. I can actually fix it very quickly. Can you see my screen again? Okay, good. Okay, so how can we translate from this 2D homogeneous space to a 1D Euclidean space, or 2D homogeneous coordinates to a 1D Euclidean coordinates? Because this is what we are doing. I mean, again, this diagram here, what represents is that we are basically taking points that are living in a specific space, in a 2D homogeneous space, and we are mapping those, or we will translate those into a different space, or into a different coordinates, in which in this case it will be Euclidean, or we will call it Euclidean. Okay, so what we do is that the y coordinate of these points here, of all the points on this space, the y coordinate acts like the w coordinates. Remember that what we did with the this hack that we did with the affine transformation matrices is that we basically add a 4th dimension, right? And we call that dimension as w. Okay, so in this case, the y information acts as the w, and the way you translate from one coordinate frame or from one space to the other space is by taking W and taking the X value divided by W. This is, again, this could be kind of confusing, but in the end what happens is this. So this line, right, is like a vector, right? So let's put your imagination right now in this point here, right? So can you see my cursor? See this point here. This point, right, is basically, it represents, its coordinates basically represent a scalar multiplied by the vector which direction is basically this line. So imagine that instead of having this line, I could have a unitary vector. So imagine that the unitary vector is, I don't know, is like an arrow here, okay? And I can multiply that vector by any scalar, either positive or negative, and by scaling that vector, I can basically move myself into this line and basically create any of these points. Do you agree? Again, if you take the direction of this line as a vector and you multiply that vector by any possible scalar, you can get to any point on this, right? So what happens if you take any of those points, right, and you take the y value and you take the x value and divide it by the y value? Where did you get? In which of these points you end up? The red one, right? You end up in the intersection in which y is equal to 1, because it's like you're kind of like normalizing everything with your y value. Okay? Okay. So, okay, quick break. Questions? Please raise your hand. I would like to hear questions with audio if it's possible. I prefer. Someone is saying that is very confused. Yes, if you're confused, please raise your hand, open the mic, and you can ask your questions. Okay, Gloria, I can hear you, I think.
Hey.
Hey.
Can you walk through an actual example using numbers for that previous point?
Give me a second. From here?
Yeah.
I mean, I didn't put those numbers here, but you can see them on the grid, right? So for example, this point here would be, oh, no. Yeah, sorry, my bad. Because my grid is actually not showing that y is equal to 1. Yeah. But again, imagine that you have a point that is basically 2 in x and 2 in y, right? So what you basically do by translating between homogeneous coordinates is you take the last coordinate of your space. So the homogeneous coordinates, what able to do is basically mapping from a n-dimensional space to a n+1 dimensional space. In this case, we were seeing kind of like the problem like backwards, because we are trying to explain it by taking the 2D to 1D. Okay? But it's
okay.
Yeah, but in this case, let's imagine that we were originally on this one-dimensional space, which is our projective line, right? So the homogeneous coordinates allows you to go from one dimension, from this n-dimensional space, one-dimensional space, to n+1 dimensional space. In this case, is a two-dimensional space, right? Or, as I was explaining, is taking a space that is n+1 dimensional and basically map everything to a one-dimensional. The thing is, in the end, what happens here is that, again, is like collapsing the space, collapsing this two-dimensional space into only one-dimensional space. And in the end, you're kind of losing information, right? Because every single point here on this line, it has the same projection on this line, on this pink line, right? That is why they call homogeneous, because their coordinates are the same when you project them into the n-1 coordinate frame. Yes? No?
Okay, that makes more sense now. Thank you.
Good. Perfect. Yeah, these topics are a bit confusing, right? Because again, this is a different type of geometry, and projective geometry is huge, and there are a lot of interesting things that can happen in projective geometry. For example, in projective geometry in 3D, what in 3D it's a parabola, for example. In projective geometry, when you convert that with using homogeneous coordinates into a 2D Euclidean geometry, from a 3D homogeneous coordinate into a 2D Euclidean geometry. What in 3D was, for example, a parabola, in 2D it turns out that it became an ellipse, right? But again, I don't want to go there because projective geometry is a huge area. This is just something very simple that you will understand eventually when we use perspectives, right? Okay, so David, yeah, so you have a question?
Yes, I'm asking if will this like x divided by w only works on y equals 1? Because if you have a different y, it won't work.
Sorry, can you repeat again? If it works when
So we have y equals 1, right?
Yes.
And how we transform from 2D homogeneous coordinates to 1D is by dividing x by its y.
Yes.
Yeah, but if we have a different y, like let's say y equals 2, but so this transformation x divided by w won't work. Is it? Or
yes, it will work. Why do you think it doesn't work? So remember, the w right now is what is the y coordinate, right? So basically, you take the y coordinate and you just name it as w, right? So for whatever point in 2D in which you have x and y coordinates, right? Just take the y coordinate, you take the x coordinate and you divide it by y, right? And you get a new x value, right?
yes.
So that x value is now your only coordinate for this one-dimensional line that is called the projective line. Right?
Okay, let's say we have point at 2, 2.
Yes.
So we divide x by its y, we get 1. That point lays
on x
y
on x equal to 1.
X equal to
yes, exactly.
1.
Because it's 2 divided by 2, right?
Yes.
So if it's 2, 2, the 1D Euclidean coordinate will be 2 divided by 2. So the coordinate will be now exactly 1. So this will be 1, right? And it's 1 in your one-dimensional coordinate, which is x, right? So it will be 1. That's it.
Yeah, but if it's y, it's not 1. Like if y is 2, then
okay. Yes, sorry. I probably misunderstand your question. So what you're saying is, what happens if the projective line is not
yes.
1? Okay, yes, you're right. That is why the projective line is always 1.
Okay.
Thank you. Yes, the projective line is always 1. Good. So it's clear now, David?
Yeah.
Good.
It's clear.
Okay, so Mark has another question. Yeah, we can. Give me a sec. Sorry. I think we can hear you, Mark. No, you're still. Yeah.
Okay. Yeah.
Yes.
Okay. So yes, I learned, for instance, slope being rise over run. So I'm wondering what would happen if you reversed it, like you divided w by x.
Your audio is kind of. I think.
Sorry. Yeah. Did you catch all of that, or was it broken up?
Can you repeat, please?
Okay, sure. So in learning about slope, I learned it as rise over run. So I'm wondering if you divided W by X instead, would you get the same result since Y is set equal to 1 in this case?
Um,
That would be x equals 1, right?
yeah, but okay, but that would be incorrect. I mean, yeah, it doesn't make any sense to just. You want to flip the division?
Yeah, I'm wondering what the result would be if you instead flipped the division. Yes.
Good question. Geometrically speaking, I mean, again, that will be incorrect in terms of projective geometry. Projective geometry, you always divide x divided by y. But okay, if you do the opposite, so if it's, I mean, if this 2 by 2, it will be the same. But if it's, yeah, it's like you moving the projective line. Okay, yeah. I mean,
Okay,
we will
I
need to
think I would-
we will need to like play with the numbers, but like
see.
formally speaking, that will be incorrect. The actual
Okay.
recipe for the projective line is y is equal to 1, and you take the y, and yeah, you take your x value and divide it by the w, but by the y value, right? I mean, formally speaking, what you have, again, homogeneous coordinates allow you to translate from an n-dimensional space to an n plus 1 dimensional space. So if you have a 3D dimensional space, which is Euclidean, you can go up into homogeneous coordinates or to a homogeneous space of 4 dimensions. So you always divide all your coordinates divided by your last coordinate. Okay?
Okay.
So I will show
I
you.
like that.
You will see that on 3D. But for now, for this 2D thing that we have here, does anyone else have questions, or is that already understood, Mark?
Yeah, I got that.
Okay, good. Okay, I think nobody else is raising hands. No one else. Okay, good. And again, we have more time for questions later. But yeah. Okay, so this is what happens in 3D. Okay, so if now we have a 3D homogeneous coordinates, right? And we have x, y, z, right? And we want to translate that into a 2D Euclidean coordinates or a 2D Euclidean space, which only has x, y. We do exactly the same recipe. And right now, instead of having a projective line, now we have a projective plane. So from all the coordinates of my homogeneous space, we take the last coordinate, in this case is z, right? And now z acts as w, right? And the way we convert from one coordinate to another type of coordinates is by taking, in this case, x, y divided by w, or in this case is divided by the z value, right? Because z is acting as a w, right? So what happens here, sorry, so Nami is asking, is this building towards a pinhole camera? Yes, exactly, Nam. This is exactly that. It's building towards a pinhole camera. Projection onto camera plane, probably. Yes. But we will need to get there like step by step, right? Yeah, so what happens here is basically the same as what we were seeing in 2 dimensions, right? Now we have a 3-dimensional space, right? X, Y, Z. And then we have a plane that its coordinate Z is equal to 1, right? So remember, the coordinate that we use, the last coordinate of the n plus 1 homogeneous space, we always make it equal to 1, okay? And then we can make this transformation, right? So this space, sorry, this plane represent the plane in which the z value is equal to 1, right? This vector here represents a one-dimensional space that it was before I was drawing the entire line, right? Now I'm not drawing the entire line. We already know that it's an infinite line, right? But I'm not drawing as an infinite line. I'm drawing it as a vector because it's like having a vector, right? We said that. It's like having a vector that has a specific direction, right? In this one-dimensional subspace. And if you multiply that vector by any scalar possible, you can get all possible points that are along that line. Do you agree? Say yes if you agree. Yes. And if you take all those points, right, that space, the space of points that are along that vector, and you collapse those points into a single point that is basically passing through that plane, right, you get the red dot. So this red dot is basically the Euclidean coordinate, the 2D Euclidean coordinate for all possible 3D homogeneous coordinates that are on this vector. I hope this, because now it's in 3D, I hope this is probably making more sense when we were seeing in 2D. So Nam is saying this is an orthographic projection. Not yet. This is not orthographic projection. This will lead us to a perspective projection, actually. Okay? So can you tell me, yes, if now this is a bit more clear, now that we are seeing this in 3D? Say yes if it's clear. Okay. Say question if you have a question, if you're still confused. Oh, nice, beautiful. So no one is confused. Perfect, great. Okay, so let's move on. Okay, so let's leave this concept here, and again, this will eventually lead us into projections. Okay, but for now, just take this as the actual origin from this homogeneous coordinate that we use to create these affine transformation matrices. Okay. Because they're not a hack, they have a meaning, and this is the actual meaning of those. Okay, so good. So now let's come back a little bit to these affine transformation matrices, and let's analyze again the difference of applying these affine transformations to either points or of vectors, right? So we're kind of shifting gears a little bit. Okay, so we said that having this alternative, this augmented matrix and this augmented vectors, we could have a linear transformation on this part of my affine transformation matrix. We can have translation, and then, oh, perfectly, and everybody's happy, and we can do whatever we want, either to point or vectors, by just adding a 1 to the point, to points, and a 0 to the W value of vectors. So now I have a question for you. So using affine transformation matrices, can we apply any linear transformation to vectors? What do you think? Remember, the linear transformation is this part of the matrix, right? So we know that the translation is already dealt by this 1 and 0, right? And so we discard the transformation in case of vectors. But what happens with these linear transformations? What do you think? Can we apply any linear transformation to vectors, or there is still some constraint when we are talking about vectors versus points? So if you think we can apply any linear transformation, say any. If you think, if not, you say no. Some, no. Okay. So here we have an example in which I have a box, right? And this box has normals, right? And we know that normals basically represent a direction that is perpendicular to or orthogonal to the surface, right? So for now, I think that is already clear. So see what happens with this transformation. What transformation is this one? Can you tell me which transformation is this one? Shear, exactly. And by the way, Nam was saying only scaling. So Nam was saying that we only need to scale. We only need to apply scaling to vectors. Let's see if that is correct. Okay, so this is skew or shear or transvection, right? Remember that there's this other weird name that nobody uses, transvection. Okay, so this is wrong, right? Because shear is a transformation that does not keep the orthogonality, right? So it does not keep angles. So in this case, the normal is wrong, right? Because it's not orthogonal to the surface anymore. So yeah, we can't use any possible linear transformation. The thing is, we can only apply orthogonal matrices, and this is I am specifically talking about normals. Okay, so remember, normals are super important in computer graphics and are incredibly, because we use normals for almost everything, and they are very relevant when we will compute, for example, shaders, the actual appearance of objects with respect to their material and everything, okay? So right now I'm talking specifically about normals. So if we are dealing with normals, what we usually do is we only apply orthogonal matrices. So can someone remind me what is an orthogonal matrix? Can you remember what is that? What is an orthogonal matrix? It's invertible, yes. That is one of the characteristics of orthogonal matrices. So remember, a transformation matrix is basically constructed by 3 basis vectors. As Michael is saying, thank you so much, Michael, those 3 basis vectors are orthogonal among them, right? Yes. Yes, Nam, exactly. So shear is also invertible, yes, but shear is not orthogonal, right? So what we care right now is the orthogonality of the matrix. So a matrix is orthogonal if its basis vectors are orthogonal, right? Which is not the case for shear, right? So yes, an orthogonal matrix is also invertible, right? But not all invertible are, in this case, orthogonal. Okay. So we could also apply uniform scale. So as Nam said that we could apply scaling, right? So uniform scale, it could also be applied because a uniform scale is basically orthogonal, right? So you basically keep the basis vectors orthogonal between them, and you're just scaling those vectors. The thing is, it doesn't make any sense to apply a uniform scale to normals because we usually, in computer graphics, what we care about normals is just their direction. So we usually want the normals to actually indicate direction, and we usually want them to be normalized. So do you remember what normalized mean in terms of vectors? What is the magnitude of a normalized vector? 1, exactly. So we usually say that the normal is the vector is normalized, or the vector is unitary, right? It means that its length it's equal to 1. And why we need to have normalized normals? Because it says, if you can say, well, if you only care about the direction, why you are like avoiding to scale them, right? The direction is not changing if you apply a uniform scaling, right? The thing is, we usually use normals, for example, to compute difference between angles. So sometimes we will use for example, for computing the angle between the normal, which is basically the surface of the object, right, with respect, for example, with the light. So the light will also create a vector, right? So if we want to compute angles, we use the dot product, right, to compute the difference between 2 vectors, and we need them to have to be unitary. Otherwise, the result of the dot product, it will not make sense in terms of angle, right? So yeah, so again, we could apply a uniform scale, but it just doesn't make any sense. So in the end, what happens with normals is that we typically only rotate normals, right? And we usually keep them normalized, right? So this is super important because it's not just like, oh, now I have this amazing tool that is affine transformations and I can apply to everything. Not to everything, and not in any case, right? So in case of normals in particular, you only apply orthogonal matrices, namely rotation matrices, right? That is the only ones that we actually care. And yeah, so and we basically need to end here because it's already 50 minutes, but I have a last question for you, which is also relevant. So in terms of a square orthogonal matrix, can somebody tell me also another important characteristic of orthogonal matrices with respect to taking the inverse of those matrices? Someone remembers something about that? There's something very, very cool about that. Nobody? Think about it. They're kind of okay. So something that is very cool about orthogonal matrices, and specifically talking about rotational matrices, is that its inverse is equal to its transpose. Exactly. Thank you, Emerson. The transpose is the inverse. Yes, that is super important. Always remember that. So every time you have a rotation matrix, right? If you want to compute the inverse of that rotation, which is basically like playing back that rotation, you will need the inverse of that matrix. But because rotation matrices are orthogonal matrices and are squared, their inverse is basically its transpose. So in terms of, yeah, like for humans, it's super easy to deal with those things, right? Because you don't need to compute anything, you just take the transpose. Okay, so we had another pause here for questions, and here I had the last part of our lecture today, which is basically an example of the first question of your theory assignment. And the thing is, sadly, we don't have any time, because we are passing the time. Remember, I always need to end 10 minutes before. So I was basically having this, basically an example of, again, similar to what we have in the theory assignment. So let me just quickly mention what it is. So this is an example of two coordinate frames, A and B, right? And we have a point P, a point Q, and a vector V. And I was just wanted to give you a little bit more hints into how to solve this in your assignment. So in the case, for example, of wanting the coordinates of the point Q with respect to B, we know that we need to construct a matrix that has the basis vectors as columns, and we need to take the inverse and multiply by the coordinate frames of Q with respect to B, but with respect to the coordinate frame A, right? So remember, when you're dealing with this type of things, you always need to think as if the coordinate frames are basically on the same origin, right? And this is one way to compute it, and the other way to compute it is as a linear combination of these basis vectors. But again, maybe I will record this as an extra video, or you will have this explanation on your labs with your TAs, okay? So basically your TAs will like give you like a jump start with your theory assignment, and I will fix the problem that we have on the current document, and I will upload it today. So yeah, someone is saying extra video is better. Yeah, maybe extra video is better. So I will try to make an extra video. Thank you so much, everybody, and I will see you on Wednesday. Bye.